Hello. So this is going to be ENGEN 102 tutorial 6. This will just be a resource for those who have tutorials in what will be tomorrow on Thursday because of Kingi Day. So there won't be any in-person tutorials running tomorrow. So instead you guys can just hopefully follow along through this Zoom recording. Okay. And you have to pick up assignments and stuff like that at your next tutorial next week. So I'll just get into some of the problems. So if you bring up assignment 6, I'll just be going through the tutorial problems at the bottom of that page. Just to note, there is a little bit of a problem with so the first question is a word problem going on about mobile phones. The second part of that question doesn't quite work out. I've done it for a couple of years and it's been the same problem, and I've found the same issue with the wording that doesn't quite work out. So I'll just do the first part of that. Okay, so with these word problems, the only difficult bit really is just extracting the useful bits of information from the problem. So we're told it costs x squared over 4 plus 35x plus $25 to produce x mobile phones per day. And if they're sold at the price of 50 minus x over 2 per phone, we need to determine what they should, how many mobile phones they should produce to maximize their profit. Okay, so first of all, we're just going to write down the useful bits. So in this problem, it's actually a little bit easier because it's sort of quite clear sort of where the variables and numbers are, which we need to jot down. Okay, so first of all, we have a cost, and everything's just going to be in dollars, but I'm not going to write in the units. We needn't be concerned with that at this stage. So the cost is x squared on 4 plus 35x plus 25. And this is to produce x phones per day. Okay, and then they tell us that the price per phone, so price, and then I'll just put in brackets per phone, is equal to 50 minus x on 2. Okay, now they're asking us about profit. So this question requires a little bit of common sense, really. So if we're thinking about this problem from the producer's point of view, they're trying to maximize their profit. Their profit is simply, and their total profit rather, is just going to be their revenue less their total cost, or just cost in this at this stage. Now, what they've given us here is total cost, okay, because that is producing X mobile phones per day. So we've already sort of factored in how many there are. So it's not the cost per phone, it's the total cost. Whereas this price that we've been told, this is per phone, it's stated explicitly. So in order to get profit, we need revenue minus cost. At the moment, we don't quite have revenue, but to get revenue's relatively straightforward again. So revenue is essentially the money you're making, you're getting in, and that's just going to be the price per phone. So 50 minus x on 2. So this is the price we receive for each phone, and then we just need to multiply that by the number of phones we sell, which is just x. Okay, and if we expand this, it's 50x minus x squared upon 2. Now, if we call profit P of x equal profit, P of x is then going to be equal to, So revenue minus cost, so we've already got revenue. If I just write it a little bit differently as the x squared term at the front, so we have negative x squared on 2 plus 50x, and then we have minus, and then all of this stuff here. Okay. Now, if you go through and simplify everything, and you put all your like terms together, you should get that profit is a function of the number of phones we produce, or not produce, the number of phones we sell, is going to be negative 3x squared on 4 plus 15x minus 25. So I've just skipped a little bit here. I haven't done the simplifying explicitly. Okay, I've skipped a step, but hopefully you can follow along there. Now, we're asked to maximize total profit. Again, this is total profit, if I haven't already said that explicitly. So to maximize anything or minimize anything, we're going to need to find the derivative. So in this case, we need to find dp by dx using Leibniz notation. And then we need to set that equal to 0. So dp by dx, and then set to 0 to find maximum. Or in this case, so maximum and minimum can just points which are called extrema in mathematics. Okay, and it doesn't, I don't think it asks for this explicitly in the question, but we're actually going to go through and prove that this is a maximum. Okay, so when we set this equal, when we set the derivative equal to 0, we just get these extrema points, which are extrema can be min or max, and that's local minimum. Okay, so it would be points like here and here rather than global maximum or minima, which are only going to be present if we define a region over which we look at a function. Okay, so I'll just get on with it and differentiate and find the derivative. So differentiating this up here, this will give us negative 3x, sorry, I shouldn't have drawn that there. We don't have the x squared anymore because we brought the power down. It's negative 3x upon 2, and then we have plus 15. And this last term is just a constant, it goes to 0. Now we let dp by dx equal 0. And this is going to give us that, if you rearrange it a little bit, we're going to get 15 is equal to 3x on 2. And solving for this, solving for x gives us that x is 10 mobile phones per day. So 10 mobile phones per day, because this is a word question, we need to sort of interpret it in the context of the question, okay, to be exactly right. So this is the number of phones they need to sell per day to maximize their profits, and that's what we think anyway. So to work out whether this point at x equals 10 is a local minimum or a local maximum, we need to actually use the second derivative test. So we need to differentiate once again and then find whether we have a negative or a positive value at this x value. So we need to evaluate what the second derivative is at x equals 10. So if we just differentiate our equation again, we actually only have a linear term here, so if we differentiate that, we're just going to get constant. So it's going to be negative 3 on 2. Now, negative 3 on 2 is obviously less than 0. So this means that because it's less than 0, this means that our curve is going to be actually what we call concave down. But in the context of looking at this point here, it doesn't actually depend on x at all, because there's no x in this equation. But logically, this must mean that the point that we've found is a local maximum. Okay, it's a little bit counterintuitive, because if our second derivative is less than 0 at a local extrema, that means that it's going to be a local maximum, and if it's greater than 0, it's a local minimum. So it's a bit counterintuitive to what you'd think. You'd think if it's a maximum, it might probably have a positive value, but that's not quite the case. Because when you go up to a maximum, it's sort of like, if you think of this like you're traveling over some sort of distance, you're sort of actually decelerating up as you get up to this point, and you continue to sort of decelerate through. So that's sort of the reasoning behind why our second derivative is less than 0 at local maxima, and vice versa for local minima. Okay, and so we found that it's a local maximum, and that's all we're going to do for this problem. So that was essentially just part A here, and I'm not going to do part B because it's not illustrative at all. It's actually, the problem falls to bits, unfortunately. So I'll just clear this off, and I'll go on with the next question. Okay, so our next question asks us to find all local extrema and inflection points for x cubed minus 3x squared minus 9x, and then we're going to describe the big picture of what you had to do to find where these occur. Okay, so, and then also additionally where the function is concave up, concave down, and then we're going to use all of this to sketch f of x. Okay, so I'll do sort of one version of how I would go about solving this problem, but do be aware that there's more than one way to skin a cat. Okay, we can do this in a couple of different ways. So we have our function x cubed minus 3x squared minus 9x. Okay, and because we want to find local extrema, we need to differentiate. So doing that, we get 3x squared minus 6x minus 9. And if we let the derivative df by dx equal 0, if I just write this out again, we can take out a common factor of 3 in all the terms. And here we've got a nice easy quadratic which we can then factorize further. Okay, so our two brackets are going to be x minus 3 and x plus 1 equals 0. All right, so if we want to set either of these brackets to be equal to 0 and sort of solve the problem, x can either be 3 or it can be negative 1. Okay, so these points are our local extrema. To actually work out whether they're local minimum and local maximum, there's no surprises here. We just need to use the second derivative test again. So differentiating again. So differentiating the first derivative to get the second derivative, we have 6x minus 6 Okay, and then if we just worry about these local extrema to begin with, so we sort of plug in each of the x values. So if we evaluate d squared f by dx squared for x equal to 3, that's going to give us 6 lots of 3 minus 6, which evaluates to 12. Now 12 is bigger than 0, so at x equals 3, we have a local minimum. Okay, and if we actually want to, because we're going to be sketching this at the end, or I'll try to on this whiteboard anyway, we need to find the exact points. So we need to, for each x value we need to find the corresponding y value, or what the function actually evaluates to at each of these points. So if we go and if we plug in 3 into this equation, we're going to get the point's going to be, or the coordinate is going to be 3, negative 27, I believe. Okay. And then if we go ahead and evaluate the second derivative at our second x value, which was an extrema, a local minimum or local maximum, plugging in -1 for x, we get -12, which is less than 0. So at x equals -1, we have a local maximum. Okay, and if we plug in -1 into our original function, we'll get a value out of 5. Okay, now we aren't quite finished with this problem. We can't quite sketch it yet because we need to, the question also asked us to find inflection points. Now, to find an inflection point, we've already got the second derivative, but we simply need to set the second derivative equal to 0. So I'll just write that out a little bit more formally. Okay, so these are inflection points, or it's points at where our function is neither concave up nor concave down. So if we go about doing that, we're going to get, so if we set this equal to 0, we get 6x minus 6 is equal to 0, and hopefully you can see that after maybe one more intermediate step, you get x is equal to 1. And if we go ahead and plug 1 into our function, find the y value for the x, for this x point, we'll get the coordinate, and it's going to be 1, negative 11. Okay. Now, at this stage, if we're doing it my way, you sort of have all the information that you require to sketch it. But the question asks explicitly, where is the function concave up? So I'll go ahead and do a couple more steps, but I'll hopefully concave up. So concave up means that the second derivative is greater than 0, and concave down the second derivative will just be less than 0. And concave up, so this sort of describes the shape of our function, and concave up sort of looks like a smiley face. Okay, so it curves upwards. So it's like a beam sagging in the middle. And concave down is like a sad face, okay? And it's sort of like a beam which is loaded from the bottom. That's called hogging, this shape. Okay. Now, to find these points, because what we have for our second derivative is just a linear function, if we want this to be greater than 0, we've already found the point where it's equal to 0, which is at 1. So if it's going to be greater than 0, x just has to be greater than 1 for our, it has to be greater than 1. And if we want our second derivative to be less than 0, x just has to be less than 1. Okay? Because we can see quite clearly if we put 1 in here, this is obviously going to be, this term on the left is going to be equal to this negative term here. So that's the point where our inflection point occurs. But if we have a larger value here, this will mean that this is going to be larger, and overall the term is going to be positive. And you can make a similar argument for why it would be negative if x is less than 1. So if we go and I'll have a go at drawing it. It's not going to be to scale or anything. So if I draw a set of axes like this, okay. Now, the way I would have done this with skipping this concave up and concave down stuff is sort of assume some prior knowledge. So this original function we have is a cubic, okay, and it's specifically it's a positive cubic, okay, so plus VE is positive, so positive cubic, and this means that it has a shape which looks like this, okay, and I just think about it like this cubic term is going to dominate over these others for large values of x. Now, because it's positive, for large values of x, it's going to be really, really positive, really large number. So that should sort of go to infinity, upward towards infinity for large values of x. And for very small or negative values of x, it should get really, really negative. Okay, so it sort of extends down towards negative infinity this way and positive infinity this way. Now, if we go and use our, first of all, we just plot our extrema. We have at -1, we have the value of 5 sort of up here. Now, that's not going to be exactly right at all. And then if we then actually, so this is our inflection point. If we go ahead and plot that, that's going to be at 1, -11. So -11 is going to look like it's somewhere around here. So -1, 5, and 1, -11. And then our last point was 3, -27. So it's going to be somewhere way down here. 3, -27. And obviously, if you've got a pen and paper, it's going to be much easier to sketch. But our graph is essentially going to look like this. And just note that at x is equal to 0, this function will also be equal to 0. So it may not look like I've done it perfectly here, but it should cross through the point 0, 0 here as well, and then it's going to curve up like this. Okay, and we can see that for x is greater than 1, so this here is our inflection point. I'll just call it IF, and then this is our local min, and this is our local max. So for x greater than 1, we've got this smiley shape here, so this is going to go off towards positive infinity, and in this range we are concave up, and then conversely over here we have the opposite shape, okay, and this is going to go off towards negative infinity. So these are sort of the regions which are concave up and concave down, and of course this is concave down as I was just explaining. Okay, and if you aren't quite familiar with what an inflection point looks like, it's just the transition between concave down, in this case concave down and concave up. So at this point, essentially, we sort of, if we take the view that obviously going up is increasing, we're increasing but at a decreasing rate, and then we reach our local maximum, and we continue to decrease all the way up until the inflection point. And this is really important because past here, we're still decreasing, but we're decreasing at a decreasing rate all the way up until our local maximum at 3, -27. And then this is the point where decreasing at a decreasing rate transitions to increasing, and it will increase at an increasing rate. Okay? Yeah, so if you've done any sort of physics, this sort of stuff should sort of make more sense of you thinking about maybe like a car driving around some sort of track, and it's decelerating and then accelerating. That's a good way to think of it. Okay, and that's all I'll do for this question. I haven't drawn it very nicely here at all. In a test, of course, you want to label it a little bit more carefully than what I've done here. Yeah, I'll just clear off this screen now. So those are the 2 questions written on the tutorial sheet. Then it tells us to do 3 other ones from a couple of pages in the textbook. I might just do a couple more problems for you guys to have a go at. So this one is just question 12A, I believe. We are given y is equal to e to the power of -x squared. Now, this function here is quite interesting. If you go onto an online grapher tool, or just if you've got a graphics calculator, you go and plot this. If we have just our set of axes here, it's going to look something rather like this. Okay, and this should have a value of 1 up here. And it's quite interesting because this shape hopefully should be somewhat familiar to you if you've done any statistics. Okay, so the shape of the curve is what we call, so a bell-shaped, it's bell-shaped, but it's a normal, it's the shape of a normal distribution, okay? Normal distribution or Gaussian distribution, okay? And in statistics, you work with curves like this, but you're going to be sort of changing their shape, so they might look a little flatter and more spread out, or they might look a little bit more thinly distributed, so that you have all your values within a smaller range, and that depends on so with this thin or thickness, it depends on sigma, which is your standard distribution, and the location of the center is controlled by the mean, mu. So I just call that mean, and the actual the exact sort of equation for this standard distribution is going to be 1 over sigma times square root 2 pi e to the -1/2, and then we have some x minus mu over sigma squared. Now this x minus mu over sigma, this is actually your zeta, or z value rather, not zeta, z. And you're probably familiar with having to do some sort of calculation here. So it doesn't look quite the same as what we've got. But essentially all it has is it's got this term at the front. So it's just some coefficient, and we've also got some other terms which are sort of coefficients of x squared. And both of these, so this coefficient out the front, this sort of just deals, it sort of tidies up another problem we run into. So a normal distribution, it has under the curve, between positive infinity and negative infinity, it will encompass an area of 1. So this basic e to the negative x squared is going to have a different area under it, but this coefficient deals with that. And then also the shape of it and where it's centered is going to be determined by this z value here. We also have this -1/2 out the front as well. But these two are sort of analogous, if you like. So we didn't need to know all that. I just thought that was a little bit interesting because in statistics you don't really see any of this, but it's quite nice to know how we actually go about doing this. So when you're finding probabilities in your calculator, you're punching in numbers, your calculator is actually going to be working with integrals using this, an equation of this form, okay? Now, we just want to know when this function, where its inflection points are. So you can imagine that it's going to have a couple of inflection points, essentially, maybe so one on this side and one on this side somewhere. So to do that, we need to find the second derivative and then set that equal to 0. So first of all, we'll just differentiate this once. So dy by dx is going to be equal to, now we have to differentiate the power in this exponential term. So negative x squared differentiates to give us -2x. And then because we have an exponential term with base e, this differentiates just to give itself. So we just have -2x times e to the -x squared. Note that they didn't ask us to find local minima or maxima, so we don't need to set this to 0 quite yet. We need to differentiate again. And differentiating at this stage proves a little bit more difficult because you'll see that we have -2x times e to the -x squared. So what we have is a product of two terms which depend on x. Okay, we have -2x and e to the -x squared. So in order to differentiate this again, we can call this term u and this term v, and we need to use the product rule when we go about differentiating this. So the product rule is d uv by dx is going to be u dash v plus uv dash, where u dash is just du by dx, and the same for v dash, that's just dv by dx. So if we go ahead and do that, u dash is just going to be, so if we differentiate this, it's just going to be -2, and we have times v, so v is just this here. And then so we've done this part, now if we do this part here, we're going to have plus u times v dash. So that's going to be -2x times, now v dash, we've already sort of found that out. So v was just this term here, and when we differentiated this term, this gave us this whole thing here. So we're going to have this times sort of the whole expression again, which is a little bit interesting. It's sort of like a recursive problem. We use the answer from before to go ahead and work out what the next one was. So if we tidy this up, we're going to get that the second derivative is e to the -x squared, and we can we'll bring a negative out here, and we're going to have 2 minus 4x squared. Now we want to find inflection points, so we have to set the second derivative equal to 0. So we're going to have negative e to the negative x squared times 2 minus 4 x squared equal to 0. Now, at this point, we can sort of neglect this exponential term, okay? So if we just think of a basic sort of exponential term like this, so e to the negative x, for example, I haven't quite drawn it right, but an exponential term is actually never going to equal 0, so we can sort of just get rid of it because we're trying to find values of x which can satisfy this equation or which will equal 0. So if we go ahead and try and find values of x for this term here, it's not going to be fruitful. So we can just sort of banish that and avoid that, and we're going to be left with 2 is equal to 4x squared. And after some rearranging, we're going to get x squared is equal to 1/2. So x is going to be equal to plus or minus 1 on root 2. And these two values here, these are our inflection points. All right, so hopefully if you hadn't quite got the gist of finding inflection points, this problem hopefully was illustrative and you've got the knack of it now. So I'll clear off the screen and I'll do one more problem. I know it said to do 3, but this next problem is going to be quite long. Okay, so I'll go on with this last problem here. So this is going to be problem, I believe it's number 10 in this set of problems. So essentially it's going to be finding inflection points again, but they sort of give us the answer and tell us to prove that these values are inflection points, and also to prove that a term that we get is going to be, well, they prove that whatever term it works out to be is the derivative. So we have y is equal to e to the negative x times sine of x. So first of all, we need to find the derivative before we work out the second derivative. This was actually the first part of the question. And again, we can see that we've got a product of two functions which are themselves functions of x. So we need to use the product rule in evaluating the derivative. So if you do that, that's going to be negative e to the power of negative x times sine of x. And then we're going to have plus e to the negative x, and then sine differentiate to give us cosine of x. However, in the problem, so it's going to make much more sense if you go online onto the textbook and look up this particular problem, but they ask us to find this derivative, but in the form a e to the negative x cosine of x plus some phase shift, which is usually denoted phi. Okay, so we just need to change what we have here into this form here. And you should be familiar with doing these sorts of things. It would have been a little bit, it might have been in the second or third week you covered this sort of stuff. But the way we go about this, so we see that we've got this e to the negative x term out the front, so we sort of just we ignore the e to the negative x terms and we look at the coefficients in front of each thing. So we've got a -1 coefficient here and we've got a 1 here, and this a, which is, if you're thinking about plotting this is going to be the amplitude of, now if we ignored the exponential term, this would just be the amplitude of our cosine waveform. Okay, so that would be a, and a is just equal to the square root of these two coefficients of sine and cosine squared. So that's going to be the square root of -1 squared plus 1 squared so that's going to be root 2. Now, if at this stage this isn't ringing any bells, hopefully you've already watched the Panoptos and have taken some notes, so you might need to consult your notes over this. Your lecturer might use a slightly different technique, but the answer you get at the end should be the same. Now, we want to find something in the form of cosine x plus phi. Now, if you go and look up either in a textbook or online, there's a trig identity for the cosine of two angles being added together, or the addition of two angles. And this should give you that cosine of x plus phi is cosine x cosine phi minus sine x sine phi. Now, what we have, if I just write down what we have, but sort of update it a little bit, because we've now found what our amplitude is, and if we rewrite this expression, I'm going to neglect the e to the negative x terms. They're always going to be there. It's not going to change the form of our solution at all, really. Or it's not going to change the important bits we need to know about anyway. We're going to have square root 2, and then because there's a square root 2 here out the front, we need to divide by the square root of 2 for each of these terms, because there's just a coefficient of 1 or negative 1 in each case. So we're going to have square root 2, and if I write the cosine term first, we can have cosine x on root 2, then we're going to have minus sine of x on root 2. So if we just deal with what's inside the brackets here, and this stuff over here, we're going to sort of, these two things are equivalent or analogous. Okay, so we have a cosine x term here and a cosine x term here, and this is an additional coefficient, cosine phi, and we also have a coefficient of 1 on root 2. So in fact, cosine phi is going to be 1 on root 2. And if we follow the same logic, we have a negative sine x term here, and we also have a negative sine x term over here. But our sine, we also have a sine phi as which is being multiplying this negative sine x term, and this sine x term is being multiplied by 1 on root 2. So sine phi is equal to 1 on root 2. So this step here is a little bit hard to follow. If you think about it for a little while, we're sort of equating these two things. We're not really worrying about what's out the front. Okay, so we're sort of working backwards to go forwards and get it into this form up here, because essentially we just need to find out what phi is going to be. Now we've got what cosine of phi and sine of phi are going to be, and to work out what phi is going to be exactly, we can plot this using a unit circle, essentially. So we have a circle like this. So sine of phi, sine is going to be our y value, okay, and cosine is going to be our x value. So if we plot our y value first, so 1 on root 2, so if it's not going to, if we plot that, this is going to be the y value, and the x value, 1 on root 2, it's actually the same, so it's up here, and we can draw a line like this, and this angle here will be phi. Now because the cosine and the sine have the sine of phi both have the same value, this means that phi is going to be equal to 45 degrees, or because in calculus we normally deal with radians, that's going to be pi on 4 radians. So all of this means that we can rewrite our original derivative in this form, and this form is going to be root 2 e to the negative x, and we have cosine of x plus phi, which is pi on 4. Okay, so, and that should be what they have in the book as what the derivative should be. Okay, so that's the first part of this problem done. Next, we need to go and actually work out where the inflection points are. So inflection points correspond to the second derivative and setting that to 0. So we need to differentiate this stuff here again. And because we've worked it out like this, it's actually a little bit easier than perhaps having to differentiate these terms here. It would be a little bit, our answer would be a little bit longer and involve a bit more working, but we've compressed it into one product. Okay, so again, we've got a product of 2x terms, so we need to use the product rule again. And if you do that, you should get that the second derivative evaluates to square root 2 times e to the negative x times cosine, hang on, negative, not cosine. We have a negative out the front because cosine goes to negative sine, so we have sine here. Okay, so I've actually just sort of doing, instead of u dash v plus uv dash, I'm writing this here is uv dash, and then if we do u dash v, that's just going to be minus root 2 e to the negative x cosine x plus pi on 4. And now we need to set this equal to 0. So to save myself some space, I'll just write equals 0 here. You shouldn't do that in your assignment, but if we let that go. So again, we're going to have a coefficient which has got an exponential term in it in both cases. So because we've got equals 0 here, we can actually just divide through by this term here, and we're not going to lose any solutions because we want to set it equal to 0, and we have a exponential term. Exponential terms are never equal to 0, so they're sort of not important to this case. So we're going to have eventually sine of x plus pi on 4 is going to be equal to negative cosine of x plus pi on 4. Now, we actually need to go ahead and use this form of trig identity again to work out what each of these are to sort of move any further forward. So if you go ahead and consult whatever source you need, it'll be this term on the left will become sine of x cosine pi on 4. And then we're going to have plus cosine of x sine of pi on 4. And that's going to be equal to this term on the right-hand side, which evaluates to negative cosine x cosine pi on 4 plus sine of x sine of pi on 4. Now, we can evaluate all the terms which have got just numeric values for the angles. Okay, so cosine and sine of pi on 4 are just going to be, that's going to be 1 on root 2. So we can write this sine of x on root 2 plus cosine of x on root 2 is equal to negative cosine on root 2 plus sine of x on root 2. Now, if we pause at this stage, we can see that we've got 2 sine of x on root 2 terms, so we can just cancel them out. And we also, so this should be cosine x, sorry. And we've got essentially 2 cosine terms, if we rearrange that, we're going to get that root 2 cosine x is equal to 0, and that's just because 2 on root 2 is equal to root 2. Okay, if we move this term over here, and we don't care about the root 2, we can just divide through by root 2, and we're going to get cosine of x is equal to 0. This is all to find the inflection points. So when we want to find the inflection points, essentially just want to find the x values at which the inflection points occur. Now, if I draw a little graph just to look at cosine, this drawing is probably not going to be too flash, but cosine is going to look something rather like this. Okay, so and we want to find where it's equal to 0, so that's where it crosses this x-axis here. So it's actually going to be off like this as well. So this value here is going to be pi on 2. This one's going to be negative, 3 pi on 2, and this value here is going to be negative pi on 2. So we can write this set of solutions for when it's equal to 0 as x is equal to pi on 2 plus n pi. Okay, because just for example, take this first solution for example, where x is equal to pi on 2. I should also write that n is an integer. Okay, so if you haven't seen, I'm sure you've seen this sort of notation before, but this funny e thing means is an element of, and then this z refers to integers. Okay, so if we take this first point, for example, we can get pi on 2 by just, for the case when n is equal to 0, and the second solution for when n is equal to 1, because that's going to be pi on 2 plus pi, which now goes to 3 pi on 2. And we can get this other solution here, or any other sort of negative solutions off in this direction, by just saying, so for this first negative solution, we can get that by saying that n is equal to negative 1, so that'll evaluate to negative pi on 2. So this is our answer for finding the points at which where inflection points occur, okay? Where inflection points occur. And that's all that this question was asking for. Okay, they actually asked you to prove it, so they would have had something very similar. I believe they had a k instead of an n, but it's just a sort of a placeholder. Okay, and that's it for this tutorial. Hopefully you got something rather out of this anyway. And if you're in my tutorial, I'll see you next week, and you'll be able to pick up assignments and tests if you haven't already picked those up. All the best with assignment 6 though. I'll see you later.